Hello. In this video I will introduce sections 2.1 and 2.2 of the Introduction to Stochastic Processes text by Kasumu. I want to emphasize that this chapter 2 is a continuation of chapter 1. Chapter 1 talks about discrete Markov chains, where you have a series of random variables x1, x2, x3, etc. And there is a transition matrix that gives relations between the probability distributions of these random variables. For example, here is a discrete Markov chain, similar to what you saw in chapter 1. In this case, my discrete Markov chain has an infinite number of states numbered from 0 to infinity. Here are my transition probabilities. At step n plus 1, the probability that xn plus 1 is equal to k depends on the probability that xn is equal to L as follows. If k is 1 more than L, then the probability is lambda over n. Lambda and n are parameters. I will discuss these later. In case when L equals k, I can replace the L here with a k, and the probability that xn plus 1 equals k, given xn equal to k, is 1 minus lambda over n. Otherwise, the transition probability is 0. We can show this with a graph. Now, let me draw my state k. My state k is here. And what this says is that if k is equal to L plus 1, that would mean that L is down here. So this is k minus 1. Okay. K equals L plus 1 is the same as L equals k minus 1. K equals L plus 1, then this transition probability here is equal to lambda over n. Okay? On the other hand, if k is equal to L, then I can have a return to the same state. This is probability 1 minus lambda over n. Now, this is just part of a transition diagram such as you did in figures 1.3, 1.4, and 1.5 in the first chapter. So you can consider this as a transition diagram, a partial transition diagram. Okay, as I said, this is like figures 1.3, 1.4, and 1.5 in chapter 1. All right? Now, given this specification for a discrete Markov chain, you should be able to do these exercises. For instance, given the 5 by 5 matrix consisting of the first 5 rows and first 5 columns of this transition matrix P. The transition matrix for this Markov chain is called P. The entries should be expressed in terms of lambda and n. Now, you remember how to do a transition matrix, right? Just to remind you, here we can have the transition matrix will look something like this. And down here we label some states. Since I want the first 5 rows and first 5 columns, the states will be 0, 1, 2, 3, and 4 here. 0, 1, 2, 3, 4. Now these states are where I'm coming from, and these states are where I'm going to. All right? So, for instance, to go from state 0 to state 0, according to the specification on this side here, that will be 1 minus lambda over n. Okay? You should be able to complete this matrix. There are more states that I'm not including in the matrix. I just want to show the first 5 by 5 for illustration. Okay? The entries will be in terms of lambda and n. Let's go back. Now, exercise 1b, show that P is a stochastic matrix. So that is that all entries of P are non-negative. That means either 0 or positive. And the row sums of P are equal to 1. Right, this should not be difficult. If you did your matrix correctly, you should be able to see this. Exercise 1c. Give the transition diagram for the first 5 states of P. Here, let me change this icon so you can see where I am. Give the transition diagram for the first 5 states of P. This is a partial transition diagram. I want you to give a complete transition diagram for the first 5 states. Okay? Exercise 1d. This is a little bit more difficult. Find an expression for the probability that xn equal to 0, given that x0 is equal to 0. Now, in other words, what is the probability that you remain in state 0 after n steps, given you started in step 0? Now, you may think about this a little bit. How can you remain in state 0? You should look in your transition diagram. If you ever leave state 0, you can never go back. If you ever leave state 0, you can never go back because the Markov chain always increases. If you look at this partial transition diagram, the arrows only go from smaller state to larger state, or they go from a state to the same state. So the only way that the Markov chain can remain in state 0, if it starts in state 0, is if it always chooses state 0. Okay? So you can use that information to do this problem. Exercise 1e. I want you to take the limit of this expression as n goes to infinity and show that you get this result. You may need some things that you know from calculus. So these are all exercises you should be able to do. Now, a continuous time Markov process takes the limit of this discrete process as n goes to infinity. That's why I chose in exercise 1e to take the limit as n goes to infinity. We may identify each step of the chain with a time interval dt equals 1 over n. If n is big, 1 over n is small. So each step of the chain is takes a very, very small time. In effect, we are dividing each unit time interval into n steps. Let me show you that over here. I have my time axis like this. And here's time 1, time 2. Now, before we had the steps of the Markov chain 0, 1, 2, 3, 4, 5. Now I assign these steps, I assign 0 here, I assign these steps to these small time intervals here. Okay? So this is step 1, and its time is dt. This is step 2, and its time is 2 dt. Okay? Continue, continue, continue. This is step n, and its time n dt. Right? But I chose dt is equal to 1 over n. So this is time 1. Okay? So I'm dividing my time into small intervals, and each interval corresponds to a transition. Now notice also that the transition probabilities are very small. If I go back to my transition probability here, lambda over n is very small because n is large. So the transition probability goes to 0, but the time for transition also goes to 0. So you have both the transition probability and the time going to 0. You may imagine, or you may compare this with derivative. When you have derivative, a numerator goes to 0 and the denominator goes to 0. So the limit is still finite. Okay. All right. So we're dividing each time interval into n steps. In other words, if I take n times t steps in the chain, that's t times n steps of length 1 over n, which brings us to t times n times 1 over n. That means time t. Okay. For this reason, for a continuous time Markov process, instead of writing x times x of tn, we'll simply write x of t. Okay. The discrete process had x1, x2, x3. The continuous process would correspond to x dt, x2 dt, x3 dt. Now, in the continuous process, we're not interested in such small times. We're interested in times like 1, 2, 3, and so on. These include many, many, many steps. Okay? So, for instance, x1 would be large n steps. So, because of the limit, we're taking many steps, and as I said, these many steps involve repeated transitions where each transition has a small probability. It is important to realize that any continuous time Markov process is the limit of a discrete Markov chain, where you take many steps and each step is a small time with small transitions. So many of the ideas associated with Markov chains also work for Markov processes. This particular Markov process that we've defined above is called a Poisson process. Now, I will continue this in the next video.